Welcome to AFD Academy. I am the instructor Arthur Francis Deban. Today we're going to be dealing with preparation of reagents which are in solid form. In our previous class we dealt with preparation of reagent in liquid form like most acids, where we deal with the volume concentration. But this time around we're going to be looking at the mass concentration, which is the concentration which we ought to deserve, or we have to first of all weigh it. All right, that one we measure using our volumetric flask, but this time around we weigh using the weigh balance. So in order to do that, like I said earlier on, most of this reagent in stock comes to the university or to the various institutions of higher learning in a concentrated form. So it is the duty of the students, the instructor, the lecturers, the technologists to prepare this reagent and have them in diluted form, which can be handled by the students. So in order to do that, you must apply certain formulas in order to be able to do that successfully without much challenges. So we're just going to go through some few examples in order to put us in the know on how to run these particular things and carry out the calculations therein. So preparation of standard solutions, in brackets solid. We want to prepare, our question number one, prepare a standard solution of 1.0 mole per dm cube of sodium triisocarbonate 4. So that is of sodium triisocarbonate 1.0 mole per dm cube. So let's start. So we want to prepare, let me write here, preparation of reagents. So our first question here says we are preparing 1.0 mole per dm cube of sodium triisocarbonate 4. So in order for us to do this, remember I said we have a formula which we use in preparing solid samples. So I have my mass concentration, which is equals to the molar count, which is given here. So I have molar count times relative molecular mass. So I have to know they've given me my molar count to be 1.0, and I have to calculate the relative molecular mass of sodium triisocarbonate 4, put them in the formula, and I proceed. So I will be having 1.0 mole per dm cube times the relative molecular mass of sodium. Sodium is 23 times 2 in the bracket, plus carbon is 12, plus oxygen is 16 times 3. So I've gotten this, so we have to calculate them out. So our 16 times 3 give us 48. So yeah, we'll be having 48 plus 12 plus 46 here. Now times my 1.0. So we know too well that it's still going to give us the same thing, right? So I have to find out 48 plus 12 plus 46. That's 106. So what I have here is 1 times that, which is 106 GDM This is the mass concentration of the sodium per 1 mole of sodium triisocarbonate 4. So it therefore means that I will be measuring 106, as in using the weight balance, measure that, and dissolve it in 1 dm cube of water. 1 dm cube is 1000 ml of distilled water. I have always said, since 106 it seems to be a very big number, what do? We reduce this. You divide it by 4 so that you can dissolve in 250 to save what? The reagent. To measure 106 grams of a particular reagent, that's a whole lot. So, and that may cost us much. Or you divide the 106 by 8. That would be probably 13.25 gram, which is reasonable. We dissolve that in 125. That makes much sense. So that is how the trend goes. So let's take another question here. Okay, now we're going to prepare 0.05 mole per dm cube of the same sample base, sodium triisocarbonate 4. So we have 0.05 mole per dm cube of sodium triisocarbonate 4. So now let's see what happens in this scenario here. We have our mass concentration. Mass con is equal to the molar con, which is 0.05 times the relative molecular mass, which we calculated earlier to be 106. So we are going to have our 106. So this is 106 times 0.05. 106 times 0.05 is equal to 5.3. So 5.3 GDN cube. So this is more reasonable because the value is a little value, which is 5.3. We measure this dissolved in 1 dn cube of distilled water. And here it shows that the concentration is not that powerful. The other one was 1 mole per dn cube. This is 0.05 mole per dn cube. So it's relatively low in terms of the concentration. So let's prepare another one, 0.1 mole per dn cube of sodium hydroxide. Number 3, 0.1 mole per dn cube of sodium hydroxide. So here we have 0.1 mole per dn cube of sodium hydroxide. So I have my mass con, which is equal to the molar con is 0.1 times the relative molecular mass. Sodium is 23 plus oxygen is 16 plus hydrogen is 1, which is 0.1 times 40 gmol. And this is equal to, I will be having then 0.1 times 40, and that will give me 4. So I have 4 GDN cube. So this becomes the mass concentration which I would, the mass which I'm going to measure using my weighing balance and dissolve in 1000 cm cube. So that's how the trend goes. This is just everything we need. If we have these formulas in our head, the principles becomes easier. So we should try the best which we can to have it stuck in our mind. So our fourth question is to prepare 0.5 mole per dn cube of potassium heptazo dichromate 6. All right, let's do that. 0.5 mole. That's question number 5. So 0.5 is what we need. Let's see that. So I have my mass con, let me write it as MC, which is 0.5 times the relative molecular mass. This is chromium, which is K2 Cr2O7. And this is 0.5 times, potassium is 39 times 2, plus chromium is 55, which is 55 times 2, plus oxygen is 16 times 7. So that's a whole lot. I will be having my 0.5 times the summation of the others, which is 39 times 2, which is 78, plus 55 times 2, which is 110, plus 16 times 7, which is 112. So when I add all of that, so I have 0.5 times the summation of that, 112 plus 110 plus 78. That is 300. Now multiply that with 0.5, which is 150. Yeah. 150 GDM3. So this is what we're going to measure to dissolve in what? 1000 ml of distilled water. We divide it by 4 and dissolve in 250, divided by 8 and dissolve in 125, as the case may be, based on what the quantity which you need. Alright? Let's take another question. Let's take 0.1 mole per dm³ potassium trioxo iodate. Okay, 0.1, yeah. Mole per dm³. That's question number 5. Where is it? Okay. Potassium trioxo iodate. Alright. Question number 5. 0.1 mole per dm³ of potassium trioxo iodate. Okay. Now we have to calculate the relative molecular mass of this. And iodine alone is 127. So I have my mass count, which is 0.1 times 39 plus 127 plus 16 times 3. This is equal to 0.1 times, I have 16 times 3, which is 48, plus 127 plus 39. I have 214. So when I multiply that with 0.1 times 0.1, so we'll be having 21.4. 21.4 GDM3. So, in case you've been asked to calculate or prepare a 0.1 mole per dm³ of potassium trioxo iodate, you know exactly that this is what you're going to do. You know the molar count which has been given to you, and the mass count, the relative molecular mass which is gotten from the compound directly. And when you do that, this is what you get. And whenever you do this, you dissolve it in 1000 cm³ of distilled water. Or if you need a little, you divide by 2, dissolve in 500, divide by 4 and dissolve in 250, or you divide by 8 and dissolve in 125, as the case may be. Let's take another one. 0.2 mole per dm³ of sodium trisulcarbonate 4. So I have 0.2 mole per dm³ of sodium trisulcarbonate 4. So my mass concentration becomes 0.1, 0.2 times the relative molecular mass of Na2CO3. Remember, we've done this before, and the relative molecular mass here is 106. So I wouldn't want to waste much time there. So 0.2 times 106. And this is equals to 0.2 times 106 is equals to 21.2. 21.2 GDM cube. So that is it. Let's take another question. Okay. Okay, let's take another one. 0.1 of potassium triisocarbonate 4. 0.1 of potassium triisocarbonate 4. So here we go again. MC here becomes, the mass concentration here becomes 0.1 times the relative molecular mass of this, 39 times 2, plus carbon is 12, plus 48, 16 times 3. So here I have my 0.1 times, so I have my 39 times 2, which gives me 78, plus 12, plus 48. Okay, that plus 12 plus 48. I have 138. So this is equals 0.1 times 138. This is times 138 is 19.044 GDM3. Let's call that 19.0 in 3 significant figures. You dissolve this in 1000, divide by 2 and dissolve in 500, divide by 4 and divide and dissolve in 250, anyone you want. That's how we go. So let's calculate 0.1 mole per dm cube of sodium chloride. 0.1 mole per dm cube of sodium chloride. Of sodium chloride. So my mass concentration becomes 0.1 times sodium is 23 plus 35.5. This is equals to 0.1, the concentration which is given, plus that. So I have my 23 plus 35.5, which gives me 58.5. 58.5. And this is equals to, when I multiply that by 0.1, I have 5.85. 5.85 GDM cube. So this should be dissolved in 1000 ml of distilled water. You know what to do when you divide by 2, 4, and 8 respectively. Alright, let's calculate 0.5 mole per dm cube of sodium oxalate. Okay, what did I say? 0.5. Okay, of sodium oxalate. Alright, so this in a bracket, put 2 outside. Now my mass concentration is 0.5 times the relative molecular mass of these times 2. So let's put it this way. Carbon is 12 plus 16. 16 times 2, because we have 2 16, plus 23, or we add 2 outside. So now 16 times 2 is 32 plus 12 plus 23. That is 67 times 2, 134. So I now have 0.5 times 134. And this is times 0.5, that gives me 67 GDM cube, which is the mass concentration. So this is the value which we're going to measure when we are preparing 0.5 mole per dm cube of sodium oxalate. So that is it. That is it. Measure this and dissolve in 1000. Let's take 0.1 mole per dm cube of ammonium chloride. What did I say? 0.1 mole per dm cube. Okay. 0.1 mole per dm cube of ammonium chloride. So I still have my mass concentration here, which is 0.1 times the relative molecular mass. Nitrogen is 14 plus 4 plus 35.5. So and base is 0.1 times 14 plus 4 plus 35.5 give us 53.5. 53.5. And this is equals to times 0.1. I have 5.35 GDM cube. So this is what you measure. Using your weighing balance, dissolve it in 1000 ml of distilled water. Alright, let's prepare 0.1 mole per dm cube of potassium hydroxide. 0.1 mole of dm cube of potassium hydroxide. So the same principle goes. I have my 0.1 times potassium is 39 plus 16 plus 1. This is 0.1 times 56. This is equals to 56 times 0.1 is equals to 5.6. 5.6 GDM cube. We measure this, dissolve it in 1000 ml of distilled water. Or it may not necessarily be distilled water, it could be any solvent you choose, probably, which you're dealing with. If, for example, I want to prepare something like a reagent or something, or a solution or whatever it is, I can dissolve it in a solvent. Let's call it methanol, it could be ethanol, it could be anything. Hexane and hexane and so on. Okay, let's take the last question here. 0.1 mole per dm cube of silver nitrate. Okay. Of silver nitrate. Okay, so our mass concentration is equal to 0.1 times. Silver has a relative molecular mass of 108. So I have my 108 plus nitrogen is 14 plus oxygen is 16 times 3. So this is equal to 0.1 times. I have my 16 times 3, 48 plus 14 plus 108, I have 170. So this is equals to, this multiply with this, times 0.1, I have 17 GDM cube. So this 17 GDM cube becomes the value which we're going to dissolve in 1000 ml of the solution which we're dealing with. Could be water, it could be methanol, or any solvent of our choice as prescribed by the manual. So this is it about preparation of reagent of solid samples. Sodium chloride, sodium hydroxide, potassium, they are all in solid form. So we measure that. When they ask you prepare 0.1 mole per DNK of sodium hydroxide, which means you don't just go measure 0.1. You have to carry out your formula, your calculations of mass concentration equals to molar contents related to molecular mass. You sort the values therein, whatever you get in it, you measure that from using your weighing balance and dissolve it in the required solvent which you are asked to deal with. And after that, probably you've gotten what you want or what you're looking for. So this is all about what we are required to do. The knowledge is important, especially in terms of preparation of reagent and in terms of our affiliation with chemistry. So I look forward that we're going to have more classes that have to deal with these areas and more. All right. So you do have a wonderful time and remain blessed.